Hi, I'm Crispy. Welcome back to Making the mangoPi, the series where I not only show you my PCB design process, but I show you the inner workings of the mangoPi. In today's episode, we're looking at the Compute Module 4 and its peripherals. Let's get started. So I've gone ahead and created a schematic for the Compute Module 4 connector, its peripherals, which these are two camera connectors, the HDMI connector, the SD card connector, the PCIe 1X connector, as well as the Ethernet. And finally, we have the 2-port USB hub integrated circuit that we'll need to hook up. Now, by itself, this looks like quite the daunting task. We have 200 pins that need to be connected on this connector and several other connections on each of these schematics. Lucky for us, the Raspberry Pi Foundation has released the schematics for the Compute Module 4 I/O board, and we should be able to reuse a lot of the design. So let's take a look at it. So I've pulled up the official datasheet for the Raspberry Pi Compute Module 4 I/O board. And if we scroll down to the table of contents, then we have a circuit diagram. If we click there, this is the schematic for how every connection is made on the Compute Module 4 I/O board. Now, lucky for us, we really don't need to change a whole lot in this schematic. We can copy a ton of it, because if you think about it, there isn't that big of a difference between the Compute Module 4 I/O board and the mangoPi revision 3. They're going to use a lot of the same peripherals, and instead of having the Compute Module GPIO pins going out to a 40-pin header, we're going to have them connect to the FPGA. So I'm going to go ahead and work through the schematic and copy the connections I need to. So I'm going to pull this to my other screen and get started. To get started, we will draw the Compute Module's PCIe and camera connections. A lot of the PCIe and camera connections are differential pairs. Differential pairs is a PCB design technique where two wires are used to transmit one signal. Differential pairs are a great choice for the high-speed communication found in the PCIe standard and the Pi's camera connections. A differential pair is created when two traces are drawn such that they have a very specific distance between them. Usually, this is in the order of a few thousandths of an inch. The PCIe port has several power connections for 12 volt, 3.3 volt, and ground. Once the differential pair and power connections are made, now we just need to mark the correct pins as no connect. That's what the green X means. Now that the PCIe connection is done, we can move on to the camera connection. As I mentioned earlier, the camera connections have several differential pairs used for sending high-speed data from the camera module to the compute module. Since the mangoPi will have two camera connectors, we will copy and paste the CAM0 connections and relabel them as CAM1. Both camera connectors share a low-speed GPIO pin. With all our camera nets created, we can actually connect the camera connectors now. A net is a term used in electronic design to refer to electrically connected points. So any pins connected to the net CAM0_D0_N should be electrically connected. The camera connections use a low-speed communication protocol known as I2C. In I2C Communication, there's a clock called SCL and a data line called SDA. In this case, the clock line is always controlled by the compute module. It generates the clock. But the data line is bidirectional, meaning that the compute module and the camera can control it. At this point, I noticed that the camera 1 had a total of 3 data differential pairs, while camera 0 only had the 1. I don't know why this is different, but this is how the compute module I/O board does it, and the people that made that schematic know way more about their own compute module than I do, so I'll defer to their design. Next, we can work on the HDMI connection. The compute module 4 actually has 2 HDMI outputs, but we will only need 1. So we can label the HDMI 1 pins as no connect, and we will create nets for HDMI 0. Once again, these are differential pairs. You can tell that a pin is a differential pair if its name ends with an _P or _N. The HDMI interface also uses the I2C Communication protocol. Now we make sure all of the camera and HDMI pins are properly connected, and we bring those nets to the peripherals page. We won't be using any of the display interfaces, so we can mark those pins as no connect. With that done, we can create the USB upstream nets. And now we just need to connect all of the ground connections. You will occasionally notice me naming a net as a bunch of question marks, or I simply name the net as whatever my question is about it. This means that I'm unsure of what to do with that pin. This is to help me see where I need to do further investigating to finish this schematic. That finishes up all of our connections on the left connector, so now we can work on the right connector. We will start by connecting the Ethernet pins and the GPIO pins. We can add an activity LED. This LED will blink when the compute module is actively doing something, such as when it is booting up. Now let's add the microSD card connections and power. We can also add an LED that tells us if the compute module's power ICs are working properly. The compute module has onboard power ICs, which means we just need to supply it with 5 volts. Then it produces the 1.8 volt and 3.3 volt. I added an R before these voltages because I want to keep these voltages separated from the other 1.8 volt and 3.3 volt networks used in the FPGA. Since the compute module 1.8 volt and 3.3 volt rails and the FPGA 1.8 volt and 3.3 volt rails are made by different power ICs, it is a good idea to keep them separate, because even a small variation in voltages would mean that the two ICs would fight each other to try and regulate the rail. With all of these nets made, we can finally go connect the microSD card connector and the Ethernet jack. At this point, I realized that I did not need these extra SD data lines, so they can be removed and replaced with no connect X's. This is a brand new Ethernet jack. The one I previously had on the board was huge and was not going to work with the form factor I was going for. One of the downsides of the new jack is that I don't really know how to read the schematic symbol, so I'm unsure about what needs to be connected and where. I'll need to do some more in-depth research to check my connections. With the Ethernet done, we can take another look at the GPIO pins. These need to be connected to the FPGA I/O bank 14. Of these GPIO pins, we will need to use one for the done signal, one for the init B signal, and one for the program B signal. We also need to make sure we have the correct SPI pins hooked up to the FPGA slave serial configuration interface so that the compute module can configure it. Once we have all the configuration pins taken care of, we can identify SPI capable pins on the compute module and make sure that their S-clock pins are connected to appropriate clock capable pins on the FPGA. These clock capable pins have a MRCC or a SRCC in their pin name. MRCC stands for multi-region clock capable. SRCC stands for single region clock capable. It should be noted that at this point, any of the FPGA I/O pins that are not clock capable or not dealing with configuration can be arbitrarily connected. This is a weird concept to think of that will make much more sense once we actually start drawing out the traces. For now, all you need to know is that these Pi bus pins will be connected to different FPGA pins once we know how everything will be laid out. Now we can start connecting the 2-port USB hub. This USB hub is very similar to the USB hub used on the compute module I/O board, so we can pretty much reuse every connection. USB hubs are fairly simple. You need to supply them with an upstream USB connection, and then the downstream USB connections can go to USB ports. The upstream connection comes from the compute module. I am adding an IC that will limit the current USB devices can sync. For the mangoPi, the USB ports will mainly be used for mouse and keyboard or for a USB to Wi-Fi adapter. None of those will need much power, so limiting the max output current is a great safety feature. And that brings us to the end of this video. In the next video, we're going to connect the rest of the FPGA I/O pins, update the SRAM schematic, update the Ethernet schematic, and draw out the PCIe schematic. Thank you so much for watching. I hope you enjoyed the video. I'll see you in the next one.